So I think it's modern now, so we'll start with the event.
चलो फिर बोलो Hi everyone, welcome to the first session of paper breakdown series. Today we'll be presenting Attention is All You Need. You can see our live stream on YouTube, and the code for this session is on GitHub. You can follow us on social media using this QR code. So this club is sponsored by GitHub. You can sign up for the student developer pack using this QR code, and you'll get paid services for free like JetBrains, Azure, and Copilot.
About the cloud format presentation.
Hello. So we are recently started Student Club for Computer Vision and Machine Learning at the University of Toronto, and we mainly do paper discussions where we usually take on recent vision papers which have been put in the past 1 week and discuss them in the club. And apart from that, we have also had conference-style research and now the first paper breakdown series. So yeah, if you want to help run our club, we are a very small club. Just feel free to drop us an email. And we also have some GitHub stickers and some pizza if you want to grab any of those while the event. And this event is also being live streamed on YouTube right now. So yeah, just a disclaimer that anything you say would be on YouTube. Yeah, so on to Aryaman and Shirish.
So this is just a brief history of artificial intelligence, starting from the electronic brain in the 1940s to transformers today, which are being used in applications like GPTs. So the previous models that were used for sequence-to-sequence models or machine translation were RNNs, LSTMs. For now, you can consider them as just black box models, where you give some input and you get some output. So the crux of the limitations of the previous models was that we weren't able to leverage the power of parallel computing. And due to fixed source representations, the flow of information in the network was hindered. So
now we'll talk more about the transformer model itself. So what the big picture walkthrough would be is basically just consider the transformer as a big black box where you pass in some input and get some output. So in the example of a machine translation case, you would pass in some input, let's say in French, and the transformer would output it back in English. So now breaking down in the box, we see that it actually is made up of two different blocks, which is the encoder block and the decoder block. So the encoder block, the task of the encoder block is basically to take the input and boil it down to vectors, which basically sum up the meaning of the sentence itself. And the decoder takes that as input and processes that into a different language or output. And in this paper, the encoding block is basically built up of 6 encoding layers, and the decoder is built of 6 decoding layers. So this is basically the entire transformer architecture in a nutshell. And that by the end of this session, we hope that you will be able to understand and implement every block of this architecture. So now starting with the input embedding block.
So a bit about neural networks. Neural networks process a list of numbers. They don't process words. And they're just basically matrix multiplication on steroids. We'll use one vector per word. So one approach is to use one hot vectors. In that, say for example, if we have a vocabulary of length m, we'll just put one at a particular index to denote the word good, and at another index to denote the word bad. But the problem is that as the size of vocabulary grows, so does these vectors. A good approach is to use word embeddings. So word embeddings are also vectors, but they don't contain zeros everywhere else. They contain non-zero numbers, and so the columns here denote the different features of related to a particular word, where the range is from -1 to 1. So for example, the word man is a singular word, and so the plural property has minus 0.7, which shows that it is not related to it. So here an example is that man is so king is closer to queen and man is closer to woman. The reason why king is closer to queen is because they're royalty, and man is closer to king because man is of masculine gender, and so is king. So this is the code for generating input embeddings. We can just in PyTorch, we can just use the nn.embedding functionality of PyTorch, and it will do everything for you. The corresponding code for this is in TensorFlow, where you will just use tokenizers dot pt tokenize to generate the embeddings. Now we'll move on to positional encoding. The reason why we use positional encoding is that embeddings don't contain information about position of word, so we have to do it manually. So we want each word to carry some information about its position in the sentence, and so the position encoding contains patterns that will hopefully be learned by our model. This is the code to generate the position encoding. So first we initialize it, and then in the forward method, we just add the embedding to the position encoding. This is the corresponding code in TensorFlow, where np.sign and np.cos are the formula for it. By summing the embedding and the encoding, we generate something known as position-aware embedding, which is basically an embedding that contains both the meaning of words and the position also. Now we'll move on to multi-head attention.
So I just want to repeat that if you feel that the coding part is going too fast, you can feel free to go to our GitHub, and you will find a notebook with very detailed comments on each function, which you can use to read. Yeah, so now moving on to the multi-head attention block. So before I start on multi-head attention, so what we can basically break it down into this graph over here. Now I'll go through each element of this graph. So before that, let's talk about what is self-attention. So what self-attention basically is, when humans see an image, they basically directly extract the most important parts of the image. They don't need to look at they don't need to look at it pixel by pixel. So that is what self-attention does. It attends to the most important parts of the input. So let's say for this image, it would be the person over here. So what self-attention does, it just extract this part, which is the important part of the image. And this is similar to a search problem where we want to search for the most important part of an image. So let's say you're just using YouTube search and you search for what are transformers and you get 3 different videos. So in this case, what are transformers? That term would be our query, and the different outputs which we get would be the keys. And we then calculate. Then YouTube basically calculates how similar the query and keys are, and then it shows you the videos which are most similar. So in this case, the second video would be most similar to our search term. So it would show me that, and that would be the value. Now just keep this analogy back in the back of your mind. And now I'll show you some more about what self-attention can be with words. So let's say I get this input, which is he tossed the tennis ball to serve. I will convert it into word embeddings and then add the position information like before to get the position-aware encoding. Then my next task would be basically to extract query, key, and value layers from this. So I will multiply the position-aware encoding with 3 different linear layers to get the query, key, and value matrices. And so for the training part, basically the query, key, and values would be equivalent. And then we want to compute pairwise similarity between each query and key. So let's say you have 2 vectors, q and k. How would you go about computing the similarity? So one of the method is basically a cosine similarity. So when you dot 2 vectors, you basically get a constant times the cos of the angle between the vectors. So over here we'll use q dot k and then divided by scale, which would basically give a constant factor of the cos between the vectors. So a larger similarity matrix would imply that the q and k are in the same direction, and a smaller value would show that they are in the opposite directions. This here we can basically replace the vectors with a matrix and use the same analogy. Then we want to make an attention weighting out of this. So if we run the softmax function on the scaled values, So softmax basically converts any value between minus infinity to plus infinity to a range of 0 to 1. So any value like, let's say 10,000 or 11,000 would get converted to like 0.9, and then any value like minus 10,000 could be converted to 0.1 or something closer to that. So it is basically a method to do that. And if we run it on this particular sentence, we would get this heat map over here, where the brighter red indicates a value closer to 1 and the duller indicates a value closer to 0. So over here, we see that the word he is related most to itself, which is very obvious, and so are all the other words. But we also observe that the word ball is very much related to tossed as well as tennis. And similarly, the word toss is related to serve. So basically, when we run softmax on this, it kind of gives the relation between each word. So it tells us which words are more related in meaning, which words are important to determine the meaning of each word. Then we want to extract the features using this attention weighting. So if we multiply this attention weighting matrix with the V matrix, we get an output. And this function is basically called the attention function, which takes in q, k, v vectors and returns the output matrix. So like I said, this is what the multi-head attention block was. And now I've shown you the self-attention block. And the self-attention is basically the same thing as a scale dot product, which can be further understood by this function, which is, and here is a graph for the same function. Once again, to reiterate self-attention with words. So for an image, when you run attention weighting, you would get something like that, where the white parts indicate values which are more important and the gray parts indicate values which are less important. And when you multiply it with the value, you would get an output which shows the most important parts of an image. Now on to multi-head attention. So if we want to get more information from a single sentence or a single image, what we do is we basically divide the sentence into h different parts and run h different self-attention blocks on each of them. So in the paper, they use h as 8. For our simple example, we just use h as 3 and consider this sentence again. And I'll break it into 3 parts as shown over here. And then I'll run self-attention head on each of these blocks, and each head, and then I'll break the query key and value matrices into 3 different blocks as well, which are q1, q2, k1, k2, and so on. Then I'll run the attention function, which I defined previously with softmax on each of the different past values, and then I'll bring it all together into one single head. I'll concatenate it and pass it through a linear layer to get it in the perfect dimension which I want. And what this will basically do is, so each head will be focusing on different parts of the sentence. So for this example, when I want to see which words are related to tossed, one of the attention head will be focused on the word tossed, another head would be focused on the word ball, and the third head would be focused on serve. So in this case, by using parallel computing and running the attention block simultaneously, I'm able to get much more information as compared to using just one attention block. And so again, with an image analogy, if this is your source image, one attention head block might focus on the person, and another block might focus on the butterfly, and a third block might focus on the bush. And here is a code for implementing this block in PyTorch. So over here, I have basically defined the different layers of the block. And I was talking about the softmax function, which has been implemented over here. And this is the same function in TensorFlow, where I have defined the QKV layers over here. And then I have then I use a function called split head to divide the input into h different heads. Then I ran scaled product attention on each of those, where I have used the softmax function again. And that basically gives then I made different classes to do that, but you can learn more about the classes and stuff on the GitHub again. Now we'll move on to the residual connection, which is this arrow over here.
So residual connections, also known as skip connections. So basically, you take the position aware embedding and you add it to the output of the multi-head attention. The advantages of using residual connection is that it helps us fight gradient vanishing problem, which basically means that during backpropagation, say for example, if the gradient is a very small number, And if you multiply a small number with a small number, then the output is a much smaller number. And a point will come when the gradients just vanish to 0. And that basically means that the model won't be learning anything. So by using residual connections, we can build deep layered networks that basically means ranging from 20 layers, 40 layers, 60 layers, and so on. This is the code for generating residual connections. In the forward method, you can see that we are adding X with the output of the sublayer, and this implements skip the residual connection. Now we'll move on to the norm part, which is short for layer normalization. In layer normalization, we take the elements of a particular layer or items of a particular layer. We compute the mean and variance of each of them, and then we calculate a new value using this formula. So the advantage of using normalization is that it helps us in a faster training, and again helps us fight gradient explosion problem, which basically means that the gradients are like very big numbers, and the output would be much bigger numbers, and the neural network would just keep diverging from points to point and won't learn anything. This is the code for doing layer normalization in PyTorch. You can see that in the forward method, we calculate the mean and the standard deviation of variance of it. And then we use the formula as described in the previous slide to calculate the new value. Now we'll move on to feed-forward networks. So again, they're just glorified matrix multiplication. And the main purpose of this network is to predict the next element of a sequence. So if you input some input sequence, this network does some processing, which is matrix multiplication, and it predicts the next word of the sequence. This is the code to generate to do the feed-forward network in PyTorch. The paper refers to the feed-forward networks as position-wise feed-forward networks, but the explanation is just the same. We use a formula as described in the paper. Now we'll move on to the encoder. So we first generate the code for the encoder block. We initialize the self-attention layer, the feed-forward network, and the residual connections for each of them. So there are 2 layers of 2 residual connections. And then in the forward method, we'll do the processing as described in the figure. And this is the whole class of it. So basically, we'll do the encoder layers 6 times. This is the corresponding code in TensorFlow. Now the output embedding is generated in the same way as input embedding. Instead of using source sequence, we'll use target sequence. The position encoding is also done in the same way. Now we move on to the masked multi-head attention. So here, the masked word here means that we are limiting our model to only look at the words that it has seen and the words before it. And this prevents the model from cheating. So how we do this is we put a very low value in the future words, and this tells the softmax function to ignore those. And this basically forces our model to predict the next words by only using the words it has already seen. So we take the query from the decoder and the keys and values from the encoder. This basically helps us to take the representation from the encoder and use it to predict the next word using the query of the decoder. This is the code for it. So we first initialize the self-attention layer, the cross-attention layer, feed-forward, and the residual connections for each of them. That is 3. And in the forward method, we compute the workings as described in the figure. This is the decoder part. Like we'll be using 6 parts, 6 decoder layers. This is the corresponding code in TensorFlow for it.
So finally, as the output of the decoder block, we are going to get a stack, and we want to basically now convert it back into words. So we'll pass it through. So let's say we are converting it in English, and let's say there are 10,000 words in English. We'll call that the variable vocab size here. So we'll pass the stack output through a linear layer, which will convert it into an array of size vocab size, and then we'll run a softmax function on it to basically predict the we basically predict the percentage or the chance of each word appearing. So when we convert it into the probability matrix, we basically get, like for this example, we get that the fifth word has the highest probability. So then we tell the model to say that the next word is basically the fifth word in the vocabulary, which in this case is am. Yeah, so this is the entire transformer class in Python, where we define each and every layer and all the encoder, decoder blocks as well. And this is the same code in TensorFlow. Once again, you can go to our GitHub to look at the code libraries, look at the code notebooks, and you can run them yourself. Now that we have designed the architecture in code, now we'll look at what actually goes through in the training and inference process. So the main advantage of using transformers, as told before, is that it uses parallel computing, and the entire training actually the entire training works through just in a single step. So let's say we want to translate we want to translate the sentence "I love you" to German. We will add in start of sentence and end of sentence token to the sentence, and we'll pass it through the encoder. It will do the positional encoding and word embedding. Then it will move on to the encoder block, and so on as described in the previous architecture. And over here in the output, we will pass in we will pass in the sentence in German with the start of sentence token present before it. So as we talked before, in the decoder itself, we have a masked attention layer, which will basically mask the words after SOS for the first iteration, and then it will mask the last two words for the second iteration, and so on. And in this way, basically, it will learn to predict it will learn to predict the word one by one in the sequence and in a single step. As now we'll walk through the inference walkthrough. So let's say in the first time step, I have given this input, which is "I love you" again in English, and I wanted to predict it in German. So this time in the output, I don't have anything to put, so I'll just put start of sentence. And now the model has learned to predict the sequence one after the other. So after getting the "I love you" input from the encoder and using the SOS output, it will predict the next word, which is basically "ish" over here. So that's how it works. And after that, for the second time step, I don't run the encoder block again. I just use the same encoder output from the first step because the input is same. But this time I change the input. This time I change the output to contain SOS as well as "ish," so that it now predicts the third word. And for the third time step, I now change the output to "ish" and "liebe," and it can predict the last word, which is "dish." And finally, I give that sentence and it learns to predict the end of sentence token. So that's about it for our discussion on attention is all you need. And you can find the complete implementation on our GitHub. And in the next term, we plan to discuss more about diffusion models as well in a similar paper breakdown series environment. And you can follow us on social media. Thank you. Yeah, please go ahead. Hmm?